From the next video, we are going to discuss the beta distribution, for which we shall need some preliminary mathematics about the beta function. It is a function defined on the positive reals cross the positive reals, that is the domain, and taking values in R. The function is denoted by this letter, which is actually capital beta, and it just looks the same as capital B. It is defined as integral from 0 to 1 of x to the power a minus 1 times 1 minus x to the power b minus 1. So a and b are the two arguments. They are both positive real numbers. So if I give you a and b, then you will compute this integral, which will be another real number, and that will be the value of beta a b. Now the first question, before we can use this as our definition, is whether we really can do this integration. Well, if you have a greater than or equal to 1 and b greater than or equal to 1, then this integrand is continuous over the closed bounded interval 0 to 1, so there is no problem integrating this at all. That is case 1. Now if any of them, at least one of them, happens to be strictly less than 1, then there might be trouble, because I have a minus 1 and b minus 1, so these exponents will become negative. As a result, it will be like 1 by x and 1 by 1 minus x. So when x goes very close to 0, that will go towards infinity. Similarly, when x goes very close to 1, this will shoot up to infinity. So case 2, if a is strictly less than 1, of course it is strictly greater than 0, then the integrand will look like this. It is going up towards infinity. I am not showing what happens near 1 because I have still not made any assumption about b. So the question is the area under this unbounded curve still a finite number? The answer is yes. Though the integral is an improper one near 0, yet we know that this improper integral, if alpha is greater than minus 1, so if alpha is less than 0 yet greater than minus 1, we know that this improper integral converges. Now, once I put a greater than 0 but less than 1, I am precisely in this situation. So the role of alpha will be played by a minus 1. So by comparison with this, we can see that this area under the curve will be finite. Now you may be wondering why I am taking half. That is nothing special. I could have taken any value between 0 and 1. So basically I am considering that part which is to the left of half, and separately I will consider that part which is to the right of half, where possible impropriety will be near 1, and that will be determined by the value of b. So I will have case 3. If b is strictly less than 1, then the integral is improper near 1. The same story holds here also. In this case, the graph will look like this. It will be unbounded near a. But whatever you can say about this, just reflect it like this. In that case, the same idea will work here also. So in place of x, you will work with 1 minus x. And b minus 1 will play the role of alpha. If b is between 0 and 1, then b minus 1 will satisfy this condition, and again you have convergence, which shows that whatever abi takes strictly positive, this quantity is always finite, and hence the beta function is well defined. The beta function has an important relationship with the gamma function, which is given by this. Beta of AB is gamma A times gamma B divided by gamma of A plus B. Now, when you remember that the gamma function is connected with the factorial, gamma of n is n minus 1 factorial for any natural number n. you notice that this is much like the choose terms. NCR, or the binomial coefficients, which are like product of two factorials, and if you add these two numbers, then the sum is n, and upstairs you have factorial of the sum. So it is very much like that, product of two gammas, and here you have gamma of the two sums, of the sum of those two numbers. So in that sense, this is kind of reciprocal of that. Now this result often helps us to compute the beta function when a and b are integers. Now we cannot prove this result in this course because this will require the bivariate change of variable in integration formula, which we have not learned yet. But once you know that technique, this proof is very simple. But let us use this fact in order to compute some beta values for integer arguments. Using these two results, find beta of 4, 5. And once you can compute this, you can easily see that you can compute it whenever these two things are positive integers.